Okay, let's jump right into this explainer. We're looking at part 1 of reading the response curve, first, second, and high-order processes. We are going to decode how you can instantly identify a system's physical behavior, literally just by looking at the shape of its trend graph. No complex math yet, just visual decoding.
So, picture this. You've got two tanks out in your facility, exact same control valve, and you hit them with the exact same step change. But when you pull up the trend, totally different stories. Tank 1 settles beautifully onto its new target in, say, 90 seconds, smooth as glass. Tank 2, it shoots way past the target, swings back down, and bounces around for 5 agonizing minutes before it finally decides to calm down.
Now, your first instinct is probably, man, something is totally broken in that second system. Or maybe the controller's gone rogue. But here's the secret. Nothing is broken in either system. They just have a different process order. And that visual shape you're staring at on the screen, it tells you absolutely everything you need to know about the physical realities of what's happening in that pipe.
Okay, so what is order? Basically, order describes how many stacked lags, or storage elements, are sitting right there between your input and your measurement. Think of every single industrial process as a capacity, like a tank that's being fed through a resistance, like a valve. The total number of those stages, that's what defines your system's order. Which brings us to our visual decoding guide. This all boils down to 3 fundamental curve shapes that you're going to see out in the field: first order, second order, and high order processes. If you can memorize these 3 shapes, you can instantly read the physics of whatever you're trying to control. Let's break them down.
We'll start with the simplest one, the first order response. A first order process is basically just a single tank filling with water. When you make a step change to the input valve, the maximum rate of change in that tank's level happens immediately. There's zero hesitation. As it fills up and gets closer to its new equilibrium, the rate of change just gradually slows down, giving you this incredibly smooth, predictable curve.
It reacts instantly, and then gently settles into that exponential curve, inching toward its final value without ever swinging past the target. In a true first-order system, you literally never have to worry about overshoot unless, the controller itself is forcing it to happen. The natural physical response is just a clean, steady climb right to the finish line. But a second-order response? That's fundamentally different because it introduces a brand new physical property to the mix: inertia. It's not just a simple tank filling anymore. It's a lot more like a car's suspension hitting a speed bump. You see this when you have 2 first-order elements interacting, or mechanical components with actual mass that resist speeding up and slowing down.
And because of that inertia, a second-order system gives you, well, complications. Depending on the damping ratio of the system, it could be underdamped, where it overshoots the target and bounces around. It could be overdamped, where it just drags and acts super sluggish. Or, in the absolute perfect scenario, it's critically damped, which gives you the fastest, smooth response possible without any of that annoying overshoot.
Then we get to high-order processes. Imagine several tanks chained together in a row, or think of a relay race. When you tweak the input at the very beginning of the chain, the front stages barely move at first. By the time that change actually works its way through all those different capacities and resistances to your sensor, you get a massive delay. But eventually, the lags catch up, and that gives you a slow, stretched-out S shape on your trend screen.
Actually, here's a great way to think about a high-order process. It's exactly like sending a text to a group chat. Your message has to pass through multiple individual attention spans before the whole group finally reacts. There's this awkward dead time where you feel like everyone ignored you, and then, bam, a sudden flurry of replies. That delay, followed by a compounding reaction, is the classic hallmark of a high-order system.
Now here's the huge insight that most people completely miss when they're pulling their hair out trying to tune a loop. Process order has absolutely nothing to do with how complicated the chemistry is or how fancy the mechanical design is. Nothing. It is purely about the number of physical storage elements, those capacities, sitting in the chain between your control valve and your sensor.
For example, you could have this massive, highly complex, multi-million-dollar chemical mixing tank, and it might actually be a super simple first-order process to control if there's only one main capacity. But on the flip side, take a simple, long-jacketed pipe that's transferring heat. You've got a thermal lag in the steam, a lag in the pipe wall, a lag in the fluid itself, and suddenly it's behaving exactly like a frustrating fourth-order process.
All right, let's do a quick test of your new visual decoding skills. Imagine you're out in the field running a step test. You bump the valve, you stare at your screen, and the measurement curve sits completely flat for 40 seconds, just doing absolutely nothing. And then finally, it starts to climb in a slow S shape. Take a second. Are you looking at a first order or a high order process?
Well, if you said high order, you nailed it. It's high order because that flat dead start is the definitive, undeniable signature of multiple lags stacked in series. Remember, a true first-order process, no matter how gigantic or slow the tank is, will always start responding immediately at its maximum rate of change. So, dead time? Dead time equals high order.
And the real danger here is human psychology, right? If an operator gets impatient during that 40-second flat start and decides to aggressively tune the controller, maybe cranking up the gain because they think the process just isn't responding, they are setting a massive trap. Because the moment that delayed, high-order reaction finally hits, all that aggressive control action will violently overcorrect, and you'll get massive oscillations. You simply cannot tune a high-order loop like it's a fast first-order loop.
So, you can now visually spot process order just by glancing at the trend shape. You know, the immediate rise of a first order, the bounce of a second order, and the flat start of a high order system. But visual reading is only half the battle. How do we precisely calculate the time it takes a process to settle? Well, the magic number in process control is 63.2%.
That 63.2% mark is the absolute key to calculating a process's time constant, which completely removes the guesswork from your tuning. In part 2 of this explainer, we are going to reveal the exact math behind it and show you how to apply it to a real-world heat exchanger. Until then, I want to leave you with this. Is your own impatience turning your control loops into oscillating disasters? Think about it, and we'll see you in part 2.